Hi everyone. First of all, I would like to apologize because I could not attend today's class because I have an important meeting with faculty. Hence, I prepare you this very boring lecture. Maybe at least you can get something beneficial from this video. So for your information, I will make a simple quiz on the upcoming lecture next week regarding this video. So please make sure you watch this video. So here again are the topics that we will go through with electrical method. So we are in the introduction part. Actually for this time, because to explain it in basic way, it's really long story. As I told you last week, electrical resistivity itself will be covering about 6 lectures alone. So we go for an introduction of resistivity methods. So basically there are 4 subtopics that we'll be discussing for this chapter, which are elementary theory, effect of homogeneous ground, electrode layout and field procedures, and interpretations. So for this lecture, we will talk about the first subtopic, which is elementary theory of resistivity survey. Before this, we have already learned about the concept of electrical survey, and this time is about the fundamental and the theory. But before that, I would like to recap about the things that we have went so far. So these are basically the concept that you should understand, the factor that will affect the resistivity of the rock. So all in all, everything is related to the electrical properties of the rock, such as the behavior of the pore, whether it is contained fluid or not, how they interconnect to each other, in terms of salinity of the fluid, so the presence of a conductive material like clays, minerals, the temperature, and so on and so forth. So this basically will influence the value of resistivity of the subsurface. So now we move to the introduction of resistivity survey. So this survey is developed by Conrad Schlumberger from France and Frank Werner from United States in early 20th century. So Conrad Schlumberger is the founder of the Schlumberger company that we already known about, this very big player in oil and gas industry for processing, quality control, and interpretation. So they actually start with the electrical resistivity first before they move on to totally on seismic and oil and gas. So they link the resistivity, which is the ability of the earth to conduct an electrical current, to subsurface electrical behavior. So they inject the direct current to the ground and start measuring potential difference from point to another point created in the earth. So from the data of electrical properties of the earth, they can derive, and is very useful because resistivity of the earth's material is varied around tens orders of magnitude, meaning that it can be distinguished easily and direct interpretation can be made based on the obtaining values. So here is the list of application for the resistivity methods. So firstly, we have exploration for mineral deposits. There are a lot of paper discussing the electrical behaviors to delineate the mineral deposit, such as sands, gravel, and clays. So this is very important to know the distribution of soil types, especially for the foundation study. And then we have a utilities investigation study, where we run the survey to identify the location of underground utilities, such as underground pipes, water supply, electrical cables or tunnel, and so on. So this is when the engineer wants to confirm that the presence of the underneath utilities for any construction and pavement or development above it. So this technically can be categorized as site investigation as well, or they call it as geotechnical engineering. So the electrical resistivity survey also rather useful in identifying waste site or landfill, to study the ground pollution, like how the liquid from the landfill penetrate or leakage to the ground and contaminate the groundwater. So cavity and karst detection, one of the famous aim of studies for resistivity survey, because the ability to detect the presence of the geohazard subsurface problem for development purpose, especially at the area with a carbonate bedrock like In KL we have KL limestone, and Ipoh we have Kinta limestone. So geological reason like glaciology also being conducted using this method, and archaeological investigation is also required this kind of technique, where we can see many papers from USM, University of Science Malaysia, using this approach, studying the buried ancient city in Lembah Bujang Kedah, so the location where you did your geofield camp. So move on to the principle of current flow in the subsurface. So in the lab, the electrical resistivity of the rock can be measured by placing the flat electrode plates on each side of cylindrical samples. In this kind of situation, we actually can simply measure resistivity of the rocks by using the Ohm's law equation, which is R equal to V over I here. However, in reality, it is not applicable when it comes into investigate the Earth's electrical properties, because we cannot put another electrode like this one to the other end of the Earth's layer. Hence, we need to consider the movement of current in vertical and horizontal ways, or horizontal distribution. Therefore, we need to consider a single current electrode and two current electrode. So in order to produce a current, we need a finite conductivity, where according to the Ohm's law, the current here, current density here is equal to conductivity times electrical field, just like what we studied from the previous lecture. So the electrical field are perpendicular to the surface of the constant voltage. So here is the electrical field propagation, we can see here, and the surface of the electrical field are perpendicular to the surface of the constant voltage V, known as equipotential line, where the direction of the electrical field is many direction, so it's going to many direction, which voltage is in circular form. So this is a kind of ray path and wave front in seismic wave propagation, where the ray path is always known as the orthogonal to the spherical wave front. So go back to the current. The voltage U here can be measured between potential difference of point P1 at this small radius here from the center, and the potential difference of point P2 at the next radius after the current density expand. So as in full, current density is actually equal to the current over area of sphere for this case, because the current density propagate in a spherical way, like the wave of seismic, meaning that as the radius here increase, so the current density somehow will decrease as it expands. So now we move to the single current electrode first. So consider the electrical current flow from a single or a simple electrode, a metal spike like here. So consider an electric current I flowing from the electrode. The air has a very high electrical resistivity, so all current will flow through the earth, so no current will flow going upward. Hence, from a symmetry argument, the current spread out uniformly in all direction in earth. So the current distribution is uniform over hemispherical shells centered at the source in the earth. So there is no electrical current moving upward, because the air has very high electrical resistivity. So all will go downward to the earth. So at a distance r from the electrode, the shell has a surface area of 2 pi r square, because it is a hemisphere propagation now, rather than a sphere that we were talking about the slides before. So the current density J is given I over 2 pi r square. So meaning that it is still the same, where J will decrease with increasing distance of current dissipate. So since we know that this equation from the previous lecture regarding the association of distance and voltage on electrical fields that actually influenced by the area towards resistivity and currents, of the material, and then we know that the voltage varies with distance r from the source by just include the resistivity of the material inside the previous equation, and we got IP over 2 pi r square. We just insert resistivity, the raw, inside the equation that we have learned just now. Okay, from this equation we just insert P because we need to consider the resistivity of the material as well. So, and integrating expressions toward voltage can be described as voltage is equal to minus I rho over 2 pi r, because it is again the supposed flow of current. So now we consider two type of electrode that are used. One with current electrodes with injecting electrical current into the earth. Another one we have potential electrode that we use to measure voltage. So the voltage between two potential electrodes A and B can be described in this very simple calculation, where delta VAB is actually equal to voltage of A minus voltage of B. So but the voltage difference actually needs to consider the distance radius between these two radius A and B by using the previous formula in order to get a resistivity value of the surface. Just now we have IP over 2 pi r. Since we have two radius here, we need to insert all these two type of radius inside the formula. Then we have 1 over r RA minus 1 over RB. So this is what we got when we rearrange the equation in order to put resistivity in your left hand side, and then we can get the resistivity of the earth. So this is essential law, Ohm's law, with a geometric factor added, and it can be measured. I will explain about the geometrical factor later on. So now we need to make sure that the electrical current is in a complete circuit. Hence we need to have two current electrode at each end. Like here we have electrode C1 and electrode C2. So take a look at this diagram. One will become injected current electrode, which is electrode C1, and another one here will become withdrawn or sink C2 electrode current or current electrode. And here we have a single potential electrode at the center that's going to measure the voltage of this injected current. So with this kind of configuration, now we can measure the potential difference of two different radius by using formula like before. So please take note that when the radius is equal for radius 1 and 2, it will become 0 on a plane equidistance between C1 and C2. So the figure here shows a quantitative evaluation of the electrical current flow pattern. So the unlabeled lines are contour of equipotential lines. Here, so this is the equipotential lines. So the line with percentage value shows the current flow lines. So electrical current flow is at right angle to the equipotential surface, meaning that they are perpendicular to the equipotential, and the electrical current does not flow directly from one electrode current to the other in a straight line. They are not travel in a straight line like this. Instead, they're going in a bend shape. This is because the charge carrier repel to each other, hence is always flow in hemispheric form. From this figure as well, we can see that the percentage of the current flow will be increasing as it goes downward, or meaning that it goes deeper. So this is again because the charge carrier are too dense at the top part, as you can see here. Hence it tends to bend downward to avoid them repel to each other. So if we look at the fraction equation here, it's stated that the current fraction IF is 2 over pi tangent minus 1 in the bracket of 2z, where the z is the depth of penetration, over A. So A is the distance between two current electrodes C1 and C2, and we can see that the current fraction is almost 50% if the depth of penetration is equal to the half of the total distance of two current electrode, meaning that the current is 50% flow when the depth of penetration is half of the total distance between C1 and C2. And we can see that the current fraction is about 70% if the depth of penetration is equal to A, meaning that if the depth of penetration 70% when the C1 and C2, A is equal to the distance A is equal to depth of penetration, meaning that the wider the spacing between two electrodes, the deeper the current will go. So again, here is the graph showing the propagation or the proportion of current flowing beneath depth of Z as a function of current electrode separation A and B. So we can say that the current flowing below the depth Z increase gradually as the separation between two potential electrodes are increasing. So however, in order to measure potential difference between these two current electrodes, it requires another two potential electrodes need to be planted that will connect to voltmeter. So the question is, why we need two potential electrodes and not just using a single potential electrode that we have learned before? So the answer is, we actually cannot measure the potential difference if we only using a single potential electrode, because potential difference only can be measured if 2 points of voltage are located at a different distance within the current electrodes, unless you put the other end of electrode that infinity outside the current electrode. Hence, basically, it is easier to measure potential difference of certain distance by using 4 electrode arrays like below. So A and B here will represent the current electrode, while M and N here is the potential electrode. So now, when it involves 4 electrodes, it is rather complicated because we have 4 radius need to be considered. Before that, we take a look the basic voltage at potential electrode 1 from this equation that we have been discussed before. So V P1 at P1, voltage at P1 can be measured as 1 or I current times rho resistivity over 2 pi in the bracket 1 minus R1. R1 is the C1 to P1 minus 1 over R2. R2 is C2 to P1. So here, when we consider the potential difference captured by potential difference of radius 1 and radius 2, where the radius 1 is the distance between C1 to P1, while the radius of 2 is the radius 2 is the distance between C2 to P1. So now we know that the potential difference delta V need to consider the voltage at P1 and P2. Hence, we also need to consider the radius of C1 to P2 and the radius from C2 to P2. So by just inserting all the required radius from 1 to 4, we can get this kind of equation, where at the end of the radius 4 will be plus because of this kind of fraction, the subtraction that change the subtraction signs or minus into plus. Therefore, we rearrange it and we can get the value of resistivity of the layer by or using this equation. So from the equation, we can simplify and make 2 pi and all the radius function or fraction as k, here. So all these 2 pi and the radius will become k, and k is a geometrical factor that depending on the distance of the 4 electrode spacings. So note that we can we got this kind of equation. We also can predict the value of potential difference in a geophysical survey. So it is a kind of solution of inverse problem, and show how the resistivity of the Earth can be computed from the field measurement of delta V, I, and electrode spacing of the geometrical factor. So here are the geometrical factor types that are depending on the way you make an array of your electrode spacings. So first we take a look on the common array, which is a Werner alpha case here, and the A part here, where it states that the geometrical factor k is equal to 2. So this is a symbol of pi a. So using the figure below, we know that the spacing of Werner arrays are equal to all electrodes. Hence you will get identical distance of A for each C1, P1, and P1 to P2, and P2 to C2. They have an equal distance, and we consider that it is A. So first we have R1 and R4 is equal to A. R1 and R4 is equal to the electrode spacing, while R2 is equal to RT, where R2 and RT is double of A. So that R2 and R3 is 2A. So when we are using the formula that we learned before, we just need to replace R1, R2, R3, and R4 with A and 2A. So it will become like this. So the result at the end, it will show that this R1 and R2, R3, all the radius will be cancelled out when you insert all the formulas to A and 2A. It will become like this. Hence it will be cancelled to each other because it is 1, and then this is what you get left, which is I rho over 2 pi A. And since we know that pi rho is equal to 2 pi A delta V over I, and using the simplified formula, we can say that the geometrical factor of the Werner alpha array is 2 pi A. Now we move to the what we so-called apparent resistivity. So if the Earth has the uniform structure, the resistivity will be equal to rho or at all points. Then the measured resistivity value will be equal to the actual or true resistivity of the Earth. However, if the resistivity of the material is variable because of inhomogeneous or an isotropic medium, that will give definitely a range of resistivity value. Hence it will be giving an average value over the region in which the current is flowing. So this average value, we call it as apparent resistivity, or P or rho A. So the apparent resistivity can be considered as the average resistivity over A volume that is located between the electrodes and in the depth range from the surface to a depth equal to the A spacings. So depend on the shape and the size of anomalous region, layering, and relative value of resistivity of the region. So it is quite similar to the equivalent resistivity of a circuit with resistors in a parallel and series. So for example, we have a parallel resistor and series resistor here. So in order to figure out how many resistors there are in the circuits and their individual resistivity, you would need to interrupt the circuit at various locations, for example at this location and this location, in order to know the voltage For series resistor, you need to put your voltmeter at this point and at this point in order to know the voltage. So with several measurements, you may able to isolate the particle circuitry. So similarly, in the earth, by changing the relative spacing and location of the potential electrode, you can unravel where the resistors are below the subsurface. So all in all, we already learned about the elementary theory and the principle of the current flow in the subsurface, and then we learned about geometrical factor, and then we learned about what is apparent resistivity, and I think that's all for this lecture. I hope we will be able to meet again on the next lecture. See you.